Alright guys, we're going to be solving another question from the first chapter of the Mechanics of Materials by Johnston, and today's question is about the concept of load and resistance factor design. So there's a section in the textbook that covers this topic, and the main takeaway from this factor design is that we're going to end up with one inequality that needs to be satisfied for this, and that inequality is that, so we have gamma d times PD plus gamma L times PL has to be less than phi times ultimate force P. So this method allows the designer to distinguish between uncertainties associated with the live load, which in here we're going to call it PL. So PL is our live load, which is the time varying load that can be supported by a structure. For example, in here we have these two guys that are walking on top of this platform, so that would be our live load. And we also have a dead load, which is the self weight of the structure contributing to the total load. So we're going to have these inequalities, and the phi in here is the resistance factor, which counts for the uncertainties associated with this structure itself, and it's normally less than 1. And we have two more coefficients, gamma d and gamma L, which are the load factors. So they account for uncertainties associated with the dead and live load. So these two normally are greater than 1, and the gamma L is generally larger than gamma d. So we're going to be solving two examples for this concept in this video and the one after this. I think in the textbook, the next question is 57, which is before this one. But look, I decided to go with this one first because it's a little bit simpler. But let's get to the question. Now that we define all these different variables that we have here. So the first line says that load and resistance factor design is used to select the two cables that will raise and lower the platform supporting these two window washers. So the platform weighs 160 pounds. So the weight of the platform is 160 pounds, which is supported by these two cables on left and right. And the weight of washers is 195 with all the equipment and everything. So 195 for each washer, which in here we have two. And these workers are free to move on the platform. 75% of their total weight will be used as the live load. So we only have 75% of the whole weight as a live load. So we have information about PL in here. And also because we have the weight of the platform 160 that is supported by two cables, so we have information about PD2. So in the A part, we assume that resistance factor phi is 0.85, so phi is known. We have gamma D and gamma L in here, so these two are knowns too. And obviously we are left off with one unknown, which is the ultimate force. So the question is asking for the required minimum ultimate load. And the reason that is asking for minimum is that because in here, if we just bring the phi on the other side of the inequality, we can see that there will be a minimum for our ultimate force because it's equal or greater than what we have on the left side of these inequalities. So which means we can change this to equal because we are looking for the minimum. And then the B part is asking for the corresponding conventional load of safety for the selected cables. So as I mentioned, it's asking for the ultimate load for one cable, and the force that the weight of the platform that we have 160 is supported by two cables. So for each cable, we're gonna have half of that. So let's start the question. So as I mentioned, we're gonna have gamma d PD is equal plus gamma L times PL is equal to 5 times PU. Because of that minimum, we're gonna go with the equal sign in here. And the rest of this, just plug in our givens into this equation. Actually, I'm gonna bring the phi on the other side. So we're going to divide that by phi is equal to where? Okay, let's start with gamma d. As I said, it's 1.2. We can see in the question 1.2 times PD. And PD, as I mentioned, is the weight of the platform that is supported by two cables. So we're gonna divide that by 2 because we have two cables. So the dead load would be half of that for each cable. So 160 divided by 2. Gamma is also 1.5. Another given, so PL is the live weight. As I mentioned, it says in the question that 75%, which is 3 over 4, would be our live. So 70%, we have 2 washers and each of them 160 pounds. 195, not 160. So this will be 195. And we're going to divide that by our phi, which is 0.85. Another given. So we can find the A part of the question, which was the minimum ultimate force. Let's just calculate this. So 1.2 times 80 plus 1.5 times 0.75 times 2 times 195. And we're going to divide that by 0.85. So our P would be 629.12 pounds. So that's the A part of the question. So the trickiest part of this question so far is just that we have to watch for this 1/2 because we have 2 cables, and in the question we have the ultimate load for 1 cable. So that's the A part, and the B part, it's asking for the corresponding conventional factor of safety. Just gonna clean up, it's too messy. So conventional factor of safety, which for that we know factor of safety is equal to the ultimate force over P. And for finding the P, we basically have the load dead plus our live load, which we already found. So 160 divided by 2 was our PD, and PL was basically 0.75 times 2 times 195. That's going to give us the P. Let's see what we get here. So 80 plus 0.75 times 2 times 195. That's going to be 372.5, and should be able to find our factor of safety now. We have 629.12 over 372.5. Let's see what we get. So this is going to give us 1.68 as the factor of safety for the B part of the question. Hope everything was clear. Let me know if you guys have any questions, and you guys take care. I'll see you in the next video. Have a good one.